Hello friends, welcome to our channel. In this lecture, I would like to show how to draw the bending moment diagram. So this is the continuation of the part 1. So see here, this is a continuous beam. For this one, based on the Kanis procedure, the obtained final moments will be here. So MAB equal to 25 kilonewton meter. So this is minus 25 kilonewton meter. That is the reason here on the beam I am applied here anti-clockwise. So you take down one note point, take anti-clockwise negative and clockwise positive. For example, MBA equal to plus 25 kilonewton meter. See here I am applying here 25 kilonewton meter, which is in clockwise direction. So here MBC equal to minus 25 kilonewton meter. That is the reason anti-clockwise. Then go for MCB. MCB equal to 45, which is in positive kilonewton meter. So I am applying here clockwise. So clockwise negative, anti-clockwise, clockwise positive, anti-clockwise negative. You always remember that note point, and then whatever the obtained final moments you applied on the beam directly like this. So based on that you can draw the bending moment diagram. So always remember one note point here, based on the fixed moments, based on the final moments, whatever obtained on the any procedure, that is in the Kanis method, slope method or moment distribution method, you can draw fixed bending moment diagram with those final moments. After that one, based on the given load, see here 50 kilonewton meter, 50 kilonewton per the point load, 15 kilonewton meter UDL and 80 kilonewton for eccentric load. So all these are the given loads. Based on this given load, you can draw the free bending moment diagram. So after that you have to club these two, you will get the final bending moment diagram, or you are also called as a resultant bending moment diagram. So if you want, you can calculate net bending moment diagram and show what are the positive bending moment and negative bending moment diagram. So first of all, I will show you here. So for the based on the given loads, how to draw the free bending moment diagram. So friends, here on the span there will be a concentrated load given exactly at the 2 meter span, means exactly at the center. So what is the shape of that for the given concentrated load? So always remember, if they are given point load, means the free bending moment diagram, the shape of the free BMD will be in the form of the triangle. So where you will get exactly ordinate point, wherever per point load, wherever the maximum load will be there. So for point load exactly wherever the point will be there, then only the maximum ordinate point will be given. So see here, this is in the form of the triangle. So and you can calculate that ordinate point. How you will get this ordinate point? So always remember, for exactly concentrated load at the center means the formula will be WL by 4. So this is the formula for calculating this ordinate point. So W is 50 kilonewton, L means length of the span, that is 4 meters, and you can take this 4 cancel means you will get 50 is that ordinate point. So you always remember this point. How you will obtain this formula means in the fixed and continuous beams, already I shown this type of derivations, how you will get for point load, for UDL and for eccentric loads. If you want, you can see that lecture, you will get clear about this topic. Then go for the UDL. So whenever a UDL is there, the shape of the free bending moment diagram will be in the form of the parabola. So what about that ordinate point formula? WL square by 8. And where you will get exactly the maximum bending moment occurs at the center of the point for the UDL. So therefore you will get exactly at the center only ordinate point. So what is that ordinate point? WL square by 8, where W equal to 15, L equal to that 5 meters, 8. If you simplify this one, you will get 47. So this is, so here the height, the ordinate will be 47, this one. Then go for the eccentric load. Here eccentric load shape also in the form of the triangle only, but here you will get exactly at the 2 meters span, but here you will get in the 5 meters span. Wherever the point load is given, there you will get the ordinate point. For example, here they will given 2.5 means you will get ordinate point at 2.5 meters, but they are not given here. That is the reason they are given 2 meters by 3 meters span. You will get exactly under the load only ordinate point. So what is the formula for this eccentrical one for calculation ordinate point? WAB by L. For example, if there will be a point load means WL by 4. So if there will be a eccentric load means WAB by L, where W equal to 80 kilonewton, A will be 2 meters, B will be 3 meters by L. So once again telling friends, all these formulas will be obtained by the fixed and continuous movement based on the derivation. So you already I uploaded some lectures on that one. So if you want, you please see that one, you will get clear the doubt how you will get these formulas. So like that you can draw the free bending moment diagram. So always remember this one. From here you can mention one scale, starting point will be 0, at the same time there will be 47, so here it will be 50, and you can go upwards 96. Like that you have to maintain some approximate scale while drawing the fixed bending moment diagram. For example, it will be 50 and you are drawing parabolic somewhat higher, and it will be 47, means it is not good. So that is the reason 50 will be somewhat higher than 47 and 96 will be higher than 50. Like that you have to maintain one approximate scale. Then move to the fixed bending moment diagram. So already I told you how to apply the moments. Anti-clockwise means negative, clockwise means positive. So friends, see here, whenever if you see that a small if I am telling you one small logic, this logic will be applicable for all types of the bending moment diagram, for drawing the bending moment diagrams. So if you see this one, this AB, so AB is a span. So whenever an anti-clockwise load, so anti-clockwise means the force will be applying on a beam like this, so downwards direction like this. So whenever a force is applied here, the beam will tend to move upwards up to how much? Here the unit force is applying as 25 kilonewton meter, that much of movement will be there, you consider that one. So the beam moved here some A dash like that. So the original position of the beam will be A dash, B, C, D. Again, if you see here, from the opposite direction, from B side, I am applying another clockwise movement on the beam. So clockwise means here it will coming and applying on this beam like that. Again this beam will be tend to move in upward direction. How much it will move? Some unit force, that is 25 kilonewton meters. Again the beam goes to B to B dash. So if you add these two, that is the bending moment diagram, that particular span. So see here, so this is the span. Whenever a force is applied at A, the beam will move upward direction like this up to some 25 kilonewton meter. That force you take as that unit force. Similarly at the same position, so then the original position of the beam will be this A, A dash and B. Again whenever an a clockwise force is applied at B, then again the B position will move to B dash. So these two are the same 25 kilonewton only. After that you can draw these two lines. So this is the bending moment diagram for the fixed bending moment diagram for the particular span AB. So you always remember, whenever a force is applying on at A in the anti-clockwise direction, so means here the force will be applied on the beam. The beam moves to the A dash. Then the original position of the beam will be A dash B. Again a clockwise force is applied at the B position. The A dash B will be position will be moved to B dash. So then the original position of the beam will be after applying the moments A dash B dash. So always remember that one. Then go to the next one. Then go to the next position, that is BC span. So I will tell you that point also. See here. See here. So here the span BC will be there. From B side, an anti-clockwise movement, that is 25 kilonewton will be there, is applied at B position. The B position will be moved to this B dash. How much it will be? That will be some 25 kilonewton meter. Similarly, a clockwise force is applied at C position. How much it will be? Some 45 kilonewton meter. So that C will be moved to some C dash. So if you club those two, you will get B dash, C dash like that. So you always remember this one. So I am showing in the drawing. So whenever a anti-clockwise force is applied at B, it will be moved to B dash. Again whenever a clockwise force is applied at C, it will move to some C dash. So here anti-clockwise means it will be applied in the downward direction to be like this here at the downward position. So it will move to up to 25. Similarly a clockwise force is applied means it will move to some C to C dash. Again you join these two. So at the B position, BA and B, so some of the movements at a particular joints will be 0. So that is the reason you will get this point minus 25 plus 25 will be same here. At the joints always remember that point also. Similarly if you go for CD, I am showing here in the board. See here, this is the CD position. Whenever an anti-clockwise force is applied on the downward direction, here what happens, the beam here moves to some C dash. How much it will be? It will be some 45 kilonewton meter. Similarly, again from the other end, 45 kilonewton load is applied here at the downward direction. So the beam tends to move in the upward direction, that is some 45 kilonewton meter, some D dash. So if you join these two lines, you will get a free bending fixed bending moment diagram. So see here in the material I will show. See here, this one. See here, you always, after drawing this one, you join these points A dash, B dash, C dash, D dash, like that, and then you can add these things, you will get the fixed bending moment diagram. Friends, I am showing one small logic here. If you apply this logic to all the moments, you will get this type of diagram. Then after that one, after obtaining fixed and free bending moment diagram, you can add, you can combinedly draw this diagram. See here, you can combinedly draw this diagram, you will obtain resultant bending moment diagram. So see here, so fixed BMD and free bending moment diagram. So fixed, in the fixed BMD only I am applying this free bending moment diagram and I am drawing same this thing. So this is the resultant bending moment diagram. If you see here, the scale will be here 25, 50 and 47 will be between 25 to 50, and for next 45 will be lesser than 47, and at the same time 25. So you always remember this scale will also somewhat lesser than 47, and this after that 45, then next 96. So what I am showing here means you please maintain some scale. For example, this 96 will be inside this 45 means it is not good. That is the reason I am telling here once again, you please maintain that one. Okay, then go for the net bending moment diagram. So here I will show how to draw the net bending moment diagram. So see here I will showing net bending moment diagram. So first of all, you see here this 25 and 25, this is the fixed bending moment diagram, and this ordinate point will be free bending moment diagram. You have to, if you want net bending moment diagram means you have to remove value from this free bending moment diagram to fixed bending moment diagram. For example, in the span AB, net bending moment means free bending moment diagram minus fixed bending moment diagram. See here, free bending moment diagram will be 50, fixed bending moment diagram will be 25. So how you will get this 25? So this is in the form of the rectangle. So if you take this ordinate point, so where I want to remove this ordinate point, I want to remove, so this 50 is the ordinate point exactly at 2 meter span. So I want to remove fixed BMD ordinate point also exactly at the point load, at the point of the point load. So here there will be center point of the point load. So I want to remove ordinate point up to here. So for example, here it will be 25, here it will be 25. So entire line wherever you take ordinate point, here, wherever you take, you will get 25 only. So for this reason I am removing this 50 minus 25 ordinate point here in the exact under the load. So 50 minus 25 will be equal to 25 kilonewton meter. For example, if you see here the span BC. So span BC ordinate point will be 47, but here at B position it will be 25 and C position it will be 45. So how you will get this one? I want exactly ordinate point at the center of the span. If I want center means what I want to do here, I want to do, so at one side the ordinate point will be 25, another side will be 45. So if I want exactly center ordinate point for the fixed bending moment means I am taking the average of that one, means 25 plus 45 by 2, you will get ordinate point 35 exactly under the load. If I am taking exactly center means you can take average. So for this trapezium you will get average point here, that is 35. So after obtaining that ordinate point exactly under the center, then you can remove in that free BMD 47 minus 35, then you will get this ordinate point, that one will be equal to 12 kilonewton meter. Then friend, go to the span CD. So here in the span CD, at C it will be 45 and at D it will be 45. For example, at C it will be 45 and at D it will be some 50 means you have to calculate ordinate point exactly for the 2 meters span. This is not center. Here, for example, for point load and parabolic one, if you take average means you will get exactly at the center, but it is not exactly at the center. For example, if you will be at 2.5 meter span means you will get, if you average means you will get that one. But here here it will be some ordinate point different, means if you want to calculate ordinate point means it was somewhat difficult. So I will show you one of the problem how you will calculate if the ordinate point is different in the eccentric load, but here there will be no such type of problem. Why? Because at C position it will be 45, at the D position it will be 45. Wherever in the entire span CD you take, for example here it will be 45 only, here it will be 45 only, here it will be at the center also 45, at the 2 meters square also it will be 45. So that is the reason for finding the ordinate point for the same ordinate for the fixed bending moment means it is not difficult here. Why? Because both are same value. So wherever you take you will get exactly same value in the entire span. Then you can remove that value in the free BMD. So 96 minus 45. So then you will get a net bending moment which is 50 kilonewton meter. So see here. So this is the positive bending moment. So these are the negative bending moment. I am mentioning clearly here. So this positive bending moment will be some 25 kilonewton meter, and here will be 12 kilonewton meter, and here will be 51 kilonewton meter. So if you want net bending moment means you can calculate like this. So in the next problem I will show you eccentric model with some different ordinate points. Then you will get clear point how you will obtain these values. So thank you for watching my channel. If you like this video, please like and share this video.